When rendering a frame, we often need to copy pixels from one render target to another. For example, if we wanted to apply some post-process effects such as bloom, we would need to blur the GPath main buffer and write the results to a new render target. To do this, we need some minimal geometry that covers the entire screen. One common method of doing this is by rendering a quad which consists of two triangles. Although this is widely used, it's a bit inconvenient to set up since we need a vertex buffer for the quad's vertices. In addition, because rasterization happens in groups of pixels, typically 4x4 pixels, this means the groups that overlap the border between the two triangles get rasterized twice, which is a wasted effort. DirectX 10 and later make it possible to fix both issues by drawing a single full-screen triangle. However, before getting to that part, I need to talk about normalized device coordinates. Object positions in a 3D scene are given in world coordinates, so any position from minus to plus infinity is possible. When viewed by the camera, only the part of the world within the camera's frustum is visible. We get the position of objects with respect to the camera frustum by doing view and perspective projections. I'll talk about these transformations in another video when we actually render 3D objects. But for now, the blue capped pyramid shape here is the result of doing these transformations. The objects outside of this frustum are clipped and not rendered in the scene. This is called the clip space. Finally, all points in the frustum are transformed in such a way that will fit within a block with normalized coordinates. I think the name is a bit misleading though, because the width and height of this block are 2 units wide. So everything that's visible to the camera is transformed into this volume. The ranges of x and y directions go from -1 to 1. In DirectX's normalized device coordinates, z goes from 0 to 1. Also note that the origin is at the center of the front face. Looking at xy plane, we can render a triangle with vertices that reach outside of the NDC volume. This way, the front face of NDC is completely covered by the triangle, whereas the region outside of it is clipped during clip space transformation. We can also assign texture coordinates to this triangle. As you can see, within the NDC, UV ranges are normalized as well. This is all there is to it, but if you'd like to know more about the graphics pipeline from the hardware's perspective, I'd recommend reading this excellent series of articles by Fabian Giesen. I can imagine this way of calculating the UV and vertex positions for the full screen triangle can be a bit confusing, so I figured I'd give a brief explanation here as well. The first part, which is determining the UV position, is fairly simple. For example, when the vertex ID is 2 and we look at the binary representation of the values, we see that the x component for text is the logical AND of vertex ID and 2, which equals 2. However, for the y component of text, we shift the bits of vertex ID to the left by 1, which effectively multiplies the vertex ID by 2, and we end up with 4. Logically ANDing 4 and 2 results in 0, which is clear when we look at the binary notation. So we get 2, 0 for text when vertex ID is 2. The second part is calculation of the vertex position using linear interpolation. As you probably know, this is the equation for linear interpolation between two values a and b, with t being between 0 and 1. So at t0 we get c equals a, and at t1 we get c equals b. When t goes from 0 to 1, then we get all values spread equally on the straight line between a and b. The HLSL's intrinsic function lerp does this operation, but apparently it also works with any value of t. When t is less than 0 or larger than 1, the lerp function will do a linear extrapolation. That is, it will give a point C that is before point A or beyond point B. Again, in case of vertex ID equals 2, For the x component, we have a equals -1, b equals 1, and t equals 2. Putting these in the interpolation formula, we see that the resulting value is 3. This way, you can compute all position values for each vertex. Here is an axis that represents the real numbers that we all know and love. R is a set that contains all integers, natural, fractional, and rational numbers. As you can see, it also includes the square root of any positive number. However, it does not include the square root of negative numbers. Because taking the square root of a negative number didn't make much sense conceptually, but was needed mathematically, the term imaginary was used to refer to these numbers. To expand the set of real numbers, a new axis for imaginary numbers was added. All real numbers are now a subset of the complex set of numbers, which consists of real and imaginary parts. Letter I can be thought of as the scale of the imaginary axis, which is equal to the square root of -1. Two complex numbers can be added in the same way real numbers are added. We add real parts and imaginary parts separately. We can think of a complex number as a two-dimensional vector. Then addition is a component-wise vector addition. Multiplication is also exactly the same, except that whenever we multiply I by itself, we get I squared, which equals -1. And the square of a complex number can be written as follows. That's it. Now you're an expert in complex number addition and multiplication. Let's see how we can use this rather uncommon skill to draw a Mandelbrot fractal. Before using complex numbers, let's have a look at this function that's simply the square of x plus a constant. We can create a series of functions in which we feed the result of the previous function into the new one. For example, if we choose x to be 0, then we get c for the first function, then c squared plus c for the second one, and so on. Choosing 0.5 for the value of c, we get 0.5, 0.75, 1.0625, and so on. As you can see, it's a rather simple exercise. Now let's generalize this function by using complex numbers. It looks pretty much the same, except z and c are now complex numbers. To evaluate the function series, we need to use complex addition and multiplication, which we just talked about. Plotting the result of each function on the complex plane, we see that for some values of c, the series will diverge to infinity, whereas for some other values, the series will either get trapped between a couple of values or converge to a finite value. If we color all divergent values white and converging or trapped values black, then we get the famous Mandelbrot fractal. Note that when we get to a point whose distance to origin is larger than 2, then we know for a fact that that point is divergent. We can also count the number of steps it took to get to a point of divergence, and depending on that number, assign a color to the starting point C. That's how we get the colorful Mandelbrot fractal. If you are interested in an infinitely more pleasing explanation, please go ahead and watch this video from 3 Blue 1 Brown. I'll put the link in the video description. Now we are ready to write the Mandelbrot fractal code. In the last video, we used this fairly simple equation to plot the Mandelbrot fractal. We saw that when we use the xy coordinates of the pixel that we are rendering for the value of c, and choosing 0 as the initial value for z, the equation resulted in z either diverging to infinity or staying within the bounds of the window for the entire number of iterations. Giving different colors to diverging and converging or trapped points makes up the fractal figure. To get the Julia set fractal, we use the same equation, but this time we will take the pixel position as the initial value for z. Remember, we always started with z equals 0 for the Mandelbrot fractal. Now, however, we use the x and y pixel coordinates. And c can be any random value on the complex plane, but as we will see shortly, we only get interesting fractals if c remains within the bounds of the Mandelbrot fractal. I found this website by Kyle Miller with a web viewer that I can use to visualize this relationship between Mandelbrot fractal and the Julia set. Here is the point C on the complex plane, and as I move it around, the resulting Julia set changes accordingly. For our shader animation, I'm going to move around the cardioid shape of the Mandelbrot fractal. I found the formula that describes the path of cardioid on this Wikimedia site. The equation is part of this image, and the meaning of W is down here. Now we are ready to write the Julia set function.